Yeah. Okay. So welcome everybody. Thank you for coming by. Yeah. So I thought I'd give a bit of a talk on embedded Rust, and this is a little bit more targeted towards like new users for embedded systems. But like if we've got some more advanced users here, I mean, I can try to answer some questions there as well. I have way too many slides, so I might go over some of them in just a high level. But if folks have more questions, don't hesitate to ask. Okay, yeah. So I wanted to cover like what is embedded. What do I mean when I'm saying embedded? What are we going to talk about today? Because that's a broader question than you might initially think. And then we'll talk about some stuff about how you work with embedded systems, so tool chains, and then we'll have a little bit of a demo with, I'll call it the blinking hello. It's kind of the hello world for an embedded system. And cover a few topics related to this. So as you get like a little bit further into embedded systems, like you'll start coming across some terms like embassy and HAL. And then we'll leave off with a few tips for getting started yourself and some additional resources you can take a look at. Okay, but back to the beginning. So what is embedded? So I got a bunch of things here. So embedded means different things to different people, but just to sort of level set. So, if you start with a laptop or a desktop computer or a server or something like that, like, is that embedded? I'm going to say just no. Most people would say no. These typically come with consumer OSs. They've got Intel, AMD CPUs. If you've got a Mac, it's probably got an ARM CPU, and they have a lot of memory these days. Phones, similarly, you might have originally considered those to be embedded systems, but these days, really, they're not. They also come with fully fledged operating systems like Android, iOS. Typically, those are ARM, and they usually have a decent amount of memory these days. So they've got, 8 gigs is typical. Some have more, some have less, but they've got a fully fledged operating system that's running them. But then once you get down into some of the other devices, like say, Wi-Fi routers, or you've got things like doorbell cameras, or even thermostat sensors, or sensors in your car, or all kinds of things. These are, broadly speaking, what I'm going to call embedded, although there's sort of still a gradient of embedded. So by that I mean, like, a Wi-Fi router, like, they'll often still have Linux, and what that means is that they've got a full OS that's got a lot of capabilities on it still. So when you're programming in Rust, it still kind of looks like you're programming for a desktop, even though maybe it doesn't have a display. Maybe it has fewer cores. Maybe it has less RAM than you used to, like, only 512 megs as opposed to many gigabytes. But then as you go down yet another layer, you might have further systems that I'll call more embedded. And these might still have an OS, but they're a lot more limited. So they're not like a Linux operating system. They're more like something like FreeRTOS, or VxWorks if you're proprietary, or there's a wide variety of them. And these start having more microcontroller-y looking CPUs, so you can find like RISC-V and PowerPC and architectures that you haven't seen either before or in a while for desktops. And the amount of memory they have is typically in the megabytes as opposed to gigabytes. So this might be single digit megabytes available to you. And then finally, there's sort of the most embedded, which I'm going to say is kind of raw metal. So you're writing Rust, and there's really very little in the way of abstraction layers between the Rust code that's running and the actual hardware in terms of registers and the pins and the memory offsets. So there's likely no operating system at all on those. And those will have CPUs like the Amiga 2560, which is the one we're going to see today. And these typically have like memory in the kilobytes, so not even the megabytes. So these devices are small enough that like they can't hold a single image from the camera on my phone, for example. And I said OS a bunch of times. So what do I mean by OS, and what does it give you that kind of goes away as you get further down the stack here? So one of the most important things is process management, preemptive or cooperative multitasking. So preemptive multitasking, obviously you have a program, you write it to do whatever it is, and the operating system is responsible for managing the resources. So when you're hogging the CPU, it'll take a little bit of that away and give that to somebody else that's trying to run on the same system at the same time. As you go down to the real-time operating systems, that typically goes away and it becomes more cooperative multitasking. So you end up having tasks as opposed to threads. Typically, that means that they've got priorities. And if you have a high priority thread, you absolutely can steal the entire CPU for as long as you want. And it's up to you to actually give that up. And that's why they call it cooperative. Hardware abstractions, again, like if you're running in Linux or Mac or Windows or whatever, the device drivers typically are very high level. You have an abstract interface that covers many different types of devices. As you get lower down, you have to care a lot more about the individual device, like what pin does what register does what, and the memory abstractions. So high-level OS, like Mac, Linux, Windows, etc. Segmented memory. If I write a program and I don't do a good job of it, I can't really crash anybody else unless they're working through one of the abstractions that the operating system supports. Like we try writing the same file at the same time or something. You can't generally write into somebody else's memory directly. As you go down to the real-time operating systems, that restriction tends to go away. It tends to be one big memory space, so you have to be better behaved. Of course, as we all know, Rust is really great at being well behaved when it comes to memory. And also, as you get to especially bare metal, the really basic memory mapping and allocation goes away. So like things like vectors and strings go away, which is, if you've never programmed an embedded system, you might be like, okay, well, what do I do if I don't have vectors or I don't have strings? Which we'll get to. Yeah, so I mostly covered this, but some examples like Linux for an embedded system. You can run Linux on devices that are not primarily computers. So I'll include that in the list, but it's really more a full OS. Like when you're writing Rust on it, it's mostly like any other program you write. Going down a level, the real-time operating systems typically have fewer helper things that the OS gives to you. So an example is you can buy like the ESP32 sets of devices, and there's all kinds of nice little packages, like little camera packages, etc., that you can buy off the shelf with these, and they are in the couple of megabytes of memory sort of range. And then there's bare metal, which is actually what we're going to see today, where we don't have any OS at all. There's just raw code and registers. Maybe at some point I'll also show what a C program looks like to kind of do the same thing. And I think you'll agree with me if you think that the Rust one looks much nicer. So okay. So working with embedded, so I mentioned there's no OSs, there's no, in this case, there's no OSs, there's no segmented memory, we're much more restricted. So how do you actually work with that? So obviously, you can't compile the system on the same system that you're running it on. So you need to work with an embedded tool chain. So you're going to put a new compiler or new front end of your compiler onto your development machine so that you can compile your code. But that has to target whatever the CPU is that you intend to run this code on. So there's a little bit of setup there, and I'll go over that. And then after that, we'll actually see some real code. Okay, so these tool chains, we're not compiling on the same computer anymore. So now we need to know what our hardware target is. So typically, when you're writing embedded, you actually know what hardware you're targeting. That may not always be true, but typically is true. And the exact compiler needed is different for every hardware target. So an AVR system is different from an embedded ARM system, is different from ESP32 system, RISC-V, for example. So we need a couple different files to configure the project. So cargo.toml, if you've programmed at Rust at all, you're already familiar with this, so we'll just kind of cover a couple settings in it, but assume you know what that is. I'll introduce a Rust toolchain toml file, and there's a cargo config toml file that they configure different parts of the build, and we have to set a few settings in each of these to make it work. Okay, so starting with just the really high level one. So cargo, people already know what most of this is. I'm just showing an example here. So you've got a package and dependencies, like that stuff is all kind of the same as what you're used to. But what you may or may not be used to is we're going to set a few features in the profile release. So the first thing we're going to do is try to optimize this for a small size, because as I mentioned, we only have kilobytes to work with here. We don't have megabytes or gigabytes to work with. And in order to do that, we're going to do a couple things. So one is we're going to set the code gen units to 1, which is this line here. That just helps the Rust compiler optimize basically in the most efficient way. So each invocation of the compiler gets the full set of code that it's going to compile, and it can produce slightly better optimizations when you do that. We are going to turn on debug. This is mostly just for the other tooling, make sure that we can get symbols, but they all get stripped out before we're going to put it on the device. We are going to turn on LTO, which is link time optimization, and we're going to put it to true, which is the so-called fat version. What this means is that after you go through the first pass of the compiler, it has to go through a linking stage. So the compiler takes the source code, turns that into object code, and then it's actually the linker that puts that together into whatever your final binary is going to be. And so while your compiler can do a bunch of optimization, there's a bunch of things that it doesn't really see until it gets to link time. And so the linker also has an optimization step, and we're turning that on in the maximum way, which means to basically consider everything. There is a thin LTO as well that basically means only do that within my crate, but we're going to do the max one that does everything. And we're going to, so opt level is optimization level. We're going to put this to S. S means small, is the mnemonic. And what that means is that, in particular, instead of optimizing for maximum performance, which is often what you do for like a desktop program, we're actually optimizing for a small binary size. Because again, this is a small device. We don't have a lot of extra space. We can't, initialize a whole bunch of different code for different struct types, for example. We want it to share as much as possible. And finally, if you've ever messed something up in Rust, which of course all of us have if we have programmed in Rust, you've seen panic at some point. And the default panic handler will print you a really nice backtrace, shows you what you did wrong, and has some options to give you even more information. We're going to turn that off. So the way you do that is you say, I want to abort. That just means I want to stop my program. That's a much simpler bit of code to do. And we'll see that panic handler in a little bit, but that's what this means. Okay, moving on to the tool chain. So this one might be new, but it's actually pretty straightforward. So this one, a lot of embedded targets, they're not first tier. So I think I have a slide that goes over what that means. But basically what that means is that every build of the Rust compiler doesn't necessarily work 100% with every single target. And so what we want to do is we want to pin it to a specific one. And a lot of the embedded targets require nightly Rust. So that's basically what we're doing here. So we're setting it to, in this case, is nightly 2025, 04, 27. This one happens to work. This came from tutorial, so I just used that one. We are using the Rust source component of the toolchain. That means that we're also pulling in the source code for the standard library so that we can compile that along with our binary. Again, the reason to do that is to try to get the smallest binary possible. And this last one, profile, just means that it's actually for the toolchain itself. It means that we don't need to pull down all the documentation and stuff because we don't care about that for this particular case. And then the last config file that I mentioned, so this is the one where we actually tell Cargo, okay, we've got a special compiler that we want to use, and we've got a special target. And that's what shows up in this build. So this first actually couple lines here, this is what's really telling the Rust compiler, okay, we're not compiling for the local machine here, we're compiling for something else. And so the target for this particular device is called AVR none. And we have to pass this additional Rust flag where we say the target CPU is an Mega 2560. Now, if you have any other CPU, you need to put whatever that CPU is here, both for the AVR, and you'll find documentation for that associated with your CPU. Just Google your device. And similarly with these, this is every specific CPU has its own moniker here. So there's a lot of different ones. You customize this to whichever hardware tool chain you're using. Next, so I'll go over flashing in a minute, but basically when you do cargo run, normally it just runs on your local machine. Again, we can't do that here because we're targeting some other machine. So there's a cool little utility called RaveDude, in this case for AVR, and there's different ones for different systems that knows how to do flashing, which is basically uploading that codes after compilation onto the device and getting it going. And finally, because we don't have a full standard library with our embedded system, we're only going to build with core. So we're doing a unstable build STD with core. Yeah, okay. So what tool chains are supported? Maybe I'll just pop this up very quickly. So this link, and I think the slides will be available after this talk. This link goes to the official Rust-Lang documentation. I'm not going to go over it. This is a giant page. There's this huge list of all the different targets. So if you go online and find some piece of hardware, it's likely your target probably shows up here somewhere. So just know that there's a lot of them, but they're organized into tiers, as I said. So the tier 1 is basically your major desktop systems. These are defined by the Rust project as meaning like everything works. So they test everything in every build. It goes through all their CI/CD pipelines. You can typically upgrade to any release and assume everything works, and you're going to be happy. They have a tier 2, which basically means they do run it as part of their builds, but they don't run all the test suites, or they only run them sometimes. It usually means they have some binary support, but not every single compiler build might work. So they might have broken builds for a little while. So you might find that you have to tinker with it a little bit, but mostly these work. So usually there's a few people looking after them, and when stuff breaks, they get fixed reasonably quickly. And then finally, there's tier 3, which I will put as, they're kind of supported, meaning somebody at some point put code in, but really nobody's standing behind it to say, yes, we guarantee that this works. Unfortunately, the one I'm demoing today falls into tier 3. So that's, one of the reasons why it's a compiler from last year. But, you should just be aware that there's the different levels of support from the Rust organization. Okay. And flashing. So again, we can't run these bits of software on the machines that we're doing the development on. So we need a way of getting, that software to the device. And typically this is called flashing. And you need some kind of hardware support for this. So in this case, the device that we'll be showing, there is actually a USB chip on the same board. The USB chip is set up so that it allows us to flash it over USB cable. And so when we get to the demo portion, we'll view that live. But just know that there's tools like RaveDude, and RaveDude is specifically available for these AVR devices. And there's quite a few different ones. RaveDude happens to be written in Rust. And they usually have good instructions for how to install it on your system. So, Rust installation is very easy, but there's some other tools that you require a package manager, or I found that most of them are in Brew as well. So, if you're on Mac, or I think it even works on Windows, you can get those tools that way. And the point of these tools is that it basically magically connects everything so that when you do cargo run, instead of running on your development machine, it actually goes run on your real piece of hardware, assuming that you've plugged it in. So that's great. Like the development experience honestly couldn't be easier for these types of things. Like I've had to fiddle with these types of tools and other projects and programming languages in the past. And I'd say like the development experience with Rust in this case is very nice. Okay, so there was a lot of talking about abstract things. So let's get into a little bit of a demo. So let's start with now, and we'll go over the code for this in a moment. But what just happened, so I did a cargo run and I did that with the screen sharing turned on. So that's all I did. I did cargo run, and while it's not super dramatic, you can see this LED is now blinking. So the LED is the program, and we'll get to the actual source code in a moment. Oh, it says your mic is off.
No, that's on my computer.
We can hear you. We can hear you.
Fine.
Oh, okay.
Yeah.
That was the automated thing. Okay.
Yeah.
So this LED is now blinking. So I just showed this part at the beginning because it's a blinking LED. So it's kind of like the hello world. Like LED is one of the simplest things that you can turn on. We will get to hopefully working LCD example in a minute or two. But I just want to show this is a very simple case right now where it's uploaded over this USB cable from the development machine just by doing cargo run. And that uploaded a program that's just blinking this LED at this frequency. So okay, so what does that look like? I'm gonna share my screen again, and I just hit Control C here, but you won't be able to see on the video, but the microcontroller still continues to do whatever it was doing. So that LED is still blinking in the background as we go here. Okay, so what does that program look like? Actually, maybe I should do this with the slides because I had it broken down. Okay, so what does the program look like? Looks like this. It's not very long. It is longer than Hello World, but this will cover most of the basic features for how to get started. In particular, I'll point out each of the lines as we go through, but there's kind of blocks if I foreshadow a little bit. So there's kind of the top matter here. So the no standard, no main, this weird panic halt thing, and there's a weird entry. And then we'll get into the peripherals, the pins, and finally the actual blinking at the bottom here. So first of all, so again, anybody who doesn't know what this is, I'm targeting it so that hopefully everybody can follow along. If you do know what some of these things are, I'll try to go through it quickly so as to not be too boring. So to start with this first declaration, so no STD. This means we don't have a standard library. And as mentioned, because we don't have things like memory support, so we don't have an allocator, for example, that's needed by a lot of standard library functions, things like the vectors and strings and all kinds of stuff. So we can't use that. But there's thankfully this little flag that says, don't link in the standard library. We still have a limited library from the Rust core. So it's called the core library, and that removes most of these functions that would be otherwise problematic. So we can just say no STD. Following that, we're getting into some of so this will be sort of weird if you've never seen this in embedded context before. So the other thing we're going to do is we're going to say there's no main function. And I'll explain what that means because, of course, you're going to say the next thing is that there is a main on this screen. So what do you mean there's no main? What this means is that we're not going to use the regular main that's generated by the compiler. We're going to do some special handling here for it. And that special handling is done. So we have a function that we've called main, but the Rust compiler won't naturally produce a binary symbol here that's main. it actually goes through this macro, and the macro expands to something that's like an extern C kind of declaration that is a wrapper around our main function, because the C function doesn't have support for a bunch of things that Rust functions implicitly do. And it's also important here that in this particular case, the return type is no return. So that's what the exclamation point means. If you've never seen it before, that means this function never ends. And for an embedded device, that's actually super important, because on a desktop machine, if your program ends either because it crashes or because it exits nicely, that's great. But what does a CPU do that has no other software running on it when it ends? There's a couple answers to that, but one of the easiest answers is, well, just don't write a function that ever ends. And finally, this weird panic halt thing. So it looks like I'm importing something and then I'm intentionally not using it, which of course is usually a warning and doesn't seem very useful to do. What this is doing is telling the compiler that it does need to link against a crate called panic halt, which is provided by the compiler. And what this does is sets up a specific function for something called panic handler, and the compiler knows what that means, and it inserts a placeholder for what the panic handler is, and then it's actually the linker that puts in the final definition. So the linker looks at the panic halt crate, and it says, oh, I see that function, and it basically copy pastes that into our final binary. So all of this stuff is actually understood mostly by the linker. The Rust compiler doesn't really need it by itself, but the linker does in order to produce a binary that can be run on our target device, because it's not a typical like Linux or Mac or Windows executable. Okay, and as we move on, so now we get into the actual code for what we're doing. So in particular, one of the first things you're going to see, and if you get into embedded programming, you see this a lot, there's a peripheral struct. And what the peripheral struct, it's part of hardware abstraction. So you'll see hardware abstraction library, or HAL, is in pretty much every board support package that you're going to see. And the reason for that is that it's the struct that contains all of the stuff that's on the same chip that our CPU is on, but it basically requires unique access to it, because you can't set a register to multiple values at the same time. It can only be set to one thing. So usually those devices are put into a peripheral struct, and so it's got a take method that basically says, okay, we're grabbing that, and this is all of the definitions of our peripherals. And then in your own source code, you have to start doling out who owns what peripherals. And this is actually great. Like Rust is awesome at this, because it's got regular ownership semantics, and the ownership semantics work very closely to the way that the hardware semantics typically work. So it's actually a awesome abstraction with ownership in Rust to make sure that at compile time, you're not messing stuff up. And yeah, so this can include anything from pins or modems like Wi-Fi, Bluetooth, ADCs or DACs, serial interfaces. Yeah, I have ACD. This should be ADC. So analog to digital converter or digital analog converter. Continuing through the source code here. So, okay, so this is basically just for demonstration what the actual type is. So, so the source code has an LED. And what the LED is, normally you just write like LED is pins D13 into output. So one of the things that you find on a lot of microcontrollers is that pins, so the actual physical wires that are going to and from the device, a lot of them are configurable. So they can be input, they can be output. Some of them can kind of be a little bit of a hybrid input-output, but you always have to put them into some mode, and there's a configuration associated with that. And in other programming languages, you have to make sure you get all of your configuration and then usage of your, say, pins correct. But in Rust, again, it's very nice because we can put this all in the type system. So the type for a pin with a different configuration is, or with an output configuration, say, is different from a pin with an input configuration. And there's a unique tag per pin. So we can put that all in the type struct, which is great because again, that feeds into the ownership. And finally, with this blinking hello example, so we're just toggling our LED on and off. There is a set high and set low. So those are typically the words that you'll see in embedded hardware. So high means it's set to a logical 1, but because there can be different voltages and things, they just say high because unless you know what the voltage is on that pin, it's not necessarily any particular number. And then there's a set low as well. So that's typically ground, but again, it depends on your wiring and it depends on other things. And then finally, if I want to do something like a sleep, I can't use the standard library stuff again. So I have to use a hardware abstraction specifically for this device that allows me to sleep essentially for 100 milliseconds. And finally, just put it all back together again. So this was the full code. So just to reiterate, most of the top stuff is really making sure that the linker is happy and that the programming tool actually knows how to get our binary onto our device and where this program should start. We've got our peripherals that control which things show up on our device. We have pins, which are the physical wires that go in and out. And then we have a configuration of those pins and the actual program that we're doing. And we can see that, Rust will do its normal verification that this function does not return. And so things like the function does not return is enforced in Rust. Now, that's kind of true, kind of untrue. We can get into a halt situation if, for example, this unwrap were to fail. And typically there's a special instruction that stops the CPU if that happens. But that's part of the panic handler. Okay, I actually do have, before we get into the next one, I have one more program that I just want to show that's maybe slightly more interesting. And try to move this around. There we go. Hopefully everybody can see that. And hopefully everybody can see the screen and the LCD at the same time. So I'm just going to do a cargo run. And we can see if I did everything correct. There we go.
Oh, that's good.
So now we have a very simple output going to this LCD. And I just have an incrementing number here just to show people it's really doing something and not just a static display. And I'll go over the source code for this briefly, but it will look very similar to this source code that we saw just for the singular pin. So source code for this one. It's a little bit longer. Trying to make this bigger so nobody gets eye strain. You'll notice that a lot of the basics are really just the same. I'm importing a couple other things here, some of which I'll go into more detail, but LCD is more complicated. So I still have my peripherals. Oops. I still have my peripherals, and I still split that out into pins. I have this new delay object, which the delay object in this case is an abstraction around the CPU. There's an internal timer thing that it can use. I'm splitting out the different pins. So you saw there was a bunch of wires. Unless people are interested, I probably won't go over the wiring diagram for this, but there's six wires that end up going to the LCD plus some power wires that don't show up in the source code. Each of these I'm turning into output because there's in this case, it's an I2C or an I2C, if you prefer, interface that goes between the main microcontroller, and there's actually another microcontroller inside the LCD that drives the images, and there's a wire protocol. Now, one of the cool things about a lot of the Rust hardware abstraction layers is that you have to know that the protocol is there so that you can use the right types, but as soon as you do that, you don't have to actually implement this from scratch. where if I were to write this in C, which would be kind of the classical example, I probably would. So there's a really cool thing here where there's this HD 44780. That's actually the other controller that's inside the LCD. And somebody wrote a driver for this. I didn't write this. That basically says, well, if you tell me what the pins are on your microcontroller, I'll just make it all work. So I'll set up, and really there's, I think this is a reset, an enable, and there's 4 data pins. That's the way you read this. And those are the ones that are used to control the other LCD. And this type knows the different instructions associated with this particular LCD and this particular controller. So I get to call really nice things that are just reset. And I have to pass this delay timer around everywhere. But really, I can say reset. So this is just take all the configuration and reset it back to its default state. And then clear. This is actually clearing the output of the LCD. And then it's got a nice write string operation that this sends the correct set of bits to select the different characters and put the different characters in the right spot. And then, so this writes our first line. And then I wanted to jump to the second line. So we've got another nice wrapper function here that says, okay, go to a specific character position. And 40 just happens to be the character position for this particular LCD. And then I wrote a different string than the one that you saw. And this was actually on purpose because it's a little bit of a debugging thing. So I put at mega 2560, that's the CPU. But then I set up this counter, and I'll go over the buffer in a moment, but really just when I go into the loop, every single time I'm in the loop, I'm calling clear, I'm incrementing my counter, I'm writing the Rust LCD and then the VAN 2026 with my output. Now, this is where you're going to start seeing some things that are a little bit different from the regular standard library. So I've got the string type, but the string type I'm getting from the heapless crate rather than the standard library crate. Why is that? And why does it have this value here? Now, I mentioned that we don't have an allocator at the moment, which means that I can't dynamically resize this in the sense of asking for more memory from the system. There is a block of memory, and I believe you can just access any offset you want in this case, but we want to, it's Rust. We want to make sure it's safe and it works and everything's done properly, and the compiler guarantees all of this for us. So heapless has a string type where you have to give it a fixed size. This is the maximum size of that string, but it's statically allocating a bunch of buffer really in the stack that says, in this case, just 16 bytes. It doesn't have to be that big. And because of that, I don't need an allocator. This is really just a nice wrapper around a fixed size array that gives me all the same string functions. So I can kind of use it the way I would have used a standard library string, but I'm using in a fixed buffer scenario. So I still get all the safety, but I'm in a more embedded context. And a lot of the helper libraries, so there's one called U format or micro format that comes with a uwrite macro. This is very similar to the standard library write macro, where you specify whatever your output thing is here. In this case, I'm using my string buffer, and I'm just using a formatter to take my integer counter and format that as a string, which I then am writing out with the write string down here in the source code. So again, it looks very similar to what you would do with a standard library, but you have to know that there's a bunch of stuff that's a little bit different here. Okay. So now I'm going to go over just high level of a couple of different libraries and helpers and kind of how this fits together. But in particular, so there's no threads, and while you could do everything as just a single threaded program, and that works fine, one of the things that people really like about the Rust ecosystem generally is async, because async is a nice model to think about stuff that you want to execute kind of out of order. So in this case, if you're used to like Tokyo, the default Tokyo runner actually allocates multiple threads in most operating systems. You can change it to a few different options, including a single threaded one, but most people don't do that because, you know, if you've got a laptop or a desktop, you got a bunch of cores, like you typically want to efficiently use as much of that as possible. But in this single threaded case, in fact, there is only one core on the CPU, so there is no parallel processing at all. But we can still use async through the help of something like Embassy. So Embassy is a crate that provides us an execution environment for async tasks, but it's all done off of cooperative multitasking. So there are no threads here. This is still all single threaded, but you can still write it as async so that you can get you know, things that kind of look like they're happening simultaneously without having to write all the timers and everything yourself. So on screen here, I've just got a really basic example. This is back to like an LED blinking. Unfortunately, Embassy doesn't properly support this particular CPU. So this example is actually just pulled directly from the Embassy README. But really, it looks very similar to the one that we just saw. So it comes with a main. In this case, Embassy has hardware support for their example device, which is a Nordic Semiconductor NRF CPU. So their equivalent of our AVR main is Embassy Executor main, but all the stuff I told you about the AVR and like how it works and how that interacts with the linker, that's all the same here. They just have their own version of that. They've got their hardware abstraction layer, which happens to be Embassy NRF in their case. And then they've got a different default constructor, but otherwise it's still roughly the same. Like this is still basically that peripherals. And you'll notice they used P, although they didn't actually spell out peripherals here. And they're able to use this to spawn tasks in the background. So they've got a blink task, and this is really just, they didn't use toggle. They used the set high and set low methods that I mentioned before. And then they've got a timer that comes from the Embassy executor. And the way that this works is that every time you see an await in this, it actually goes back to a single global executor, an Embassy, that keeps track of all the tasks that have been registered to it. And it goes through and it manually pulls them to see whether they're ready to go or not. And it, I believe, tries to do it in like a round robin fashion. So it'll go to the next one always until it finds one that's ready to go. So we spawn a task that initially, I mean, we might get to the first await statement and that's spawning the task. And then it goes to await, and then it goes, oh, well, there's a timer, there's a hardware timer that needs to wait for 150 milliseconds. So it's going to block. It probably sets a hardware register in the background, and then it moves on. At which point it would go to our button. And then in this case, they have a button that you can press the button simultaneously. And if you actually had this hardware, you could press the button and you could see this log being emitted of button pressed at the same time that you'd see the LED blinking on and off at roughly 150 millisecond cadence. So Embassy is actually really nice for that. It gives you async if you're using, you know, async functions. It's fully supported. Again, it's very nice, but you do have to have a little bit more capable hardware than this particular microcontroller. And then the other one, just to go a little bit more detailed. So there's embedded HAL. Embedded HAL is actually it's a crate name, but the crate mostly provides traits. So it's kind of like how like the SerDes crate has a bunch of traits that then there's like SerDes JSON and SerDes, a whole bunch of different things that each implement those traits so that you can get the different output formats. Embedded HAL is kind of the same idea, but it's for like low-level I/O stuff. So you typically have often three different crates associated with a hardware device. So one is a peripheral crate. These are typically the lowest level. That somebody went through the data sheet and they copied a really long and boring table that says this register means that. And they provide source code that lets you reference those with slightly nicer names. Then there's a hardware abstraction layer crate that uses the traits from embedded HAL to actually give you nicer features on top of the peripheral. So that's similar to the LED blink. So the LED toggle thing that I showed earlier, this was using an AVR crate that was providing a HAL layer. And that gives you kind of the next level up of easy to use. So you don't have to work with really low level like numbers. It gives you functions that you can do specific actions with. And then there's high level driver crates, like the LCD driver that I showed you, that they're pin agnostic. They're actually hardware agnostic. So they've got certain requirements, like they might say, like the one I demoed had an I2C interface, and it says, okay, I work over an I2C interface. All I2C interfaces kind of work the same way. However, with different chips, there's different pins that come into play, or different config setups that you have to do, and so that's where the HAL crate comes in. So I could use that the HD 44780 struct in order to drive my LCD, even though the writer of that crate didn't specifically know that I was going to use it with this piece of hardware. So it's this is roughly true for most embedded devices. So you can see that the ecosystem connects things together relatively nicely. And a brand new feature, it's kind of like cut off on the bottom of the screen here, is that embedded HAL has a new 1.0 version that now supports async natively, which is also a kind of nice feature that it has. So previously you needed something like Embassy. More and more of that is being expressible at the HAL layer as well. So you can actually have HAL functions that are async now. Oh, I guess that was where I thought I'd do the LCD demo. And maybe I'll just show one pain point. And I just want to use this as a point of comparison. So if you wrote that LCD, so again, just to remind people, like we have a relatively nice, like we set up some pins, we set up a struct, and then we were able to do write string here. This is what it would look like in C. You'd have a bunch of defines with a bunch of these names that, unless you have the data sheet in front of you, I don't know what they are, especially, there's port H, port B, DDR, HB, whatever those mean. You have to worry about doing things like sending pulses with specific delays in order to send commands. If you want to send a nibble, so you can't even send a whole byte at a time, you can only send 4 bits at a time over this interface. You got to care about that, and you got to do some bitwise logic, which you can then write a nice LCD write higher up. But again, that HAL layer that we have in Rust, where it abstracted away which pin is which, like I basically hard-coded that here with the only abstraction being my defines at the top. And then you have to send a bunch of numbers, and it's kind of annoying. And I will admit that I didn't get this to work. Now, this is a thing about Rust. I just want to compare, like, if you've done something similar, and I won't say this is an expert example either, but if you did something similar in, say, C, this is the kind of code you'd be working with. And I personally find the Rust version to be much, much nicer and easier to read. Okay, so I hinted at a few things. So no STD. Unfortunately, a lot of crates really do depend on the standard library. So you often have to go find alternatives for stuff that that you otherwise would have used the standard library for. Now, a couple good ones, heapless, we already covered, and there's a whole bunch of different structs in here, which we can't see at the top level, I guess. It does say there's vex and string. Oh, here we go. So it re-implements a lot of the standard library types, which again, I won't bore everybody with the details. You can go read this yourself, and the links will be in the slides when they're posted. Static cell for global statics with no STD. That's quite useful. FMT is a formatting library that apparently is also faster than the standard library one, supposedly. I haven't benchmarked it myself, but they make that claim on their site. So if you're also looking for something that's a little bit faster than a standard library, you could also consider that. You can use no standard compatible crates on standard library stuff, no problem. So it's only hard going in the other way. And maybe I'll skip the embedded storage, but I will show people that there's this actually really awesome embedded Rust GitHub that just on the README here, they're just collecting all of the different things that have, well, so everything from community chat rooms to, if I scroll down, like if you want to use an STM CPU, for example, here's all the different crates that they've found for, the STM devices and the Texas Instruments devices and Giga devices. Anyways, they've got lots of CPU data. They've linked data sheets. There's a library section. So here's the no STD crates. Again, I won't bore people with this list. Just know that the list is very large. A bunch of things for panic handling, for specific things you might want, and various, firmware projects, books, etc. So if you're interested in doing something and you've got some idea in your mind about, hardware that you might want to use, or you're running into some problem with your embedded Rust project, I'd say, go check out that page. Just skim it, even to see if there's something that you think is interesting. That's a great resource. And finally, and I think this is my last slide, tips for getting started. Basically, just start trying stuff. Like, get yourself some hardware. So it's not quite as low level as the one I've demoed here, but I actually personally really like Espresso's ESP32 kits. They come with free RTOS on them. So you can actually use the standard library part, so you don't have to worry quite as much about the no STD parts with these. But the other thing is they're cheap. They're on the order of $15 Canadian. You can get them on Amazon or at hobby stores, pretty much anywhere. There's all kinds of peripherals you can attach to them, and there's pre-built dev kits for just trying stuff out, so you don't have to be an expert at soldering electronics or anything like that. And they kind of look like this. So this is just one example. I'm not endorsing this particular vendor, but ESP32, and you basically just go find the ones that have peripherals that you want to work with. And then another one, if you really don't know what you want to do, but you want to like play around with stuff, one thing that's cool is Elegoo has something that they call the most complete starter kit, Mega 2560. That's what this board that I demoed today came from. But just to give an example, so this is like the product page for it. So it comes with all kinds of resistors, peripherals. It's got a couple motors. It's got a number of sensors. It's got like some microphones. It's got a temperature sensor. It's got a RFID. It's got, here's the LCD that we use. There's some like pin inputs, a whole bunch of stuff. So if you really want to go and play with a bunch of different hardware and kind of see what it can do, and want something that's mostly kind of complete out of the box, that you don't have to go searching around hobby stores for all kinds of different electronics, I would recommend picking up a kit like this. And they're a little bit more expensive, like $90 Canadian kind of thing, but you can potentially spend a lot of hours on it, so it can be money well spent. And that's it for the prepared slides. Hopefully people thought it was interesting. And thank you.
All right, can you mute? Am I did I unmute the? Okay, yeah, it's unmuted. Cool. Just checking. Let's see, we've got a couple of messages in chat. So much nicer in Rust compared to C. Yeah.
Yeah, I mean, I will admit I didn't spend a lot of time on the C one, and I actually had Gemini generate that for me. It did not work out of the box, and I spent about 10
Nice.
minutes fiddling with it and fixing some pins, and it still didn't work, so I dropped it. But yeah,
Interesting.
but that's what Gemini thinks a device driver should look like in C.
Of course. Cool. So for async runtimes, do you have to use like I don't know, does Tokyo have like a no standard runtime or something, or like do you have to use something special?
So I think Tokyo, well, it doesn't have a no STD option, I don't think. And it's relatively heavyweight. Like it pulls in a lot of code. So that's where like something like Embassy shines, where it's much much smaller. But like Embassy has the problem, and actually I see Cassie has the fog question, like any notable pain points using Rust for embedded. So one of the main ones is that people have been doing embedded projects in C forever. So it is true that if you're using some really niche piece of hardware, C probably has better tooling support for it and libraries that people have written. Embassy, I did kind of play around with it because in theory I can kind of hack it to work on this device, and I wasn't able to get it to work because there were missing pieces. So when stuff is missing, it can be a little bit frustrating. It's easy to say like be careful with your hardware choices, but sometimes you can be pretty far into a project before you realize that some particular device isn't well supported. And then in a lot of ways, you're not really that much worse off, but it means you have to go back and start digging into the data sheets associated with your piece of hardware. And you can write all of those abstraction layers that I mentioned. Like you can write them yourself, and they're approachable in the sense that once you look at one or two, you kind of know how to write all of them. And I haven't tried, but maybe the AI tooling is actually really good for that kind of like rote work, just going from data sheet to base definitions. But I'd say that's probably the major pain point that I found. In many ways, I found programming with Rust was actually nicer than C because you get all those really nice error messages in before you try uploading to your device. And you have to be more careful in the hardware world because if you get your wiring wrong and you accidentally short something, you could damage it in a way that you have to buy a new one, which you don't have that with pure software. So Rust is actually kind of nice to kind of save you from some of those things, but it can't save you from everything. So you still have to kind of pay attention. Yeah, bit shifting in C. One thing, so that's absolutely true. One thing that well, again, maybe this is less of an issue with some of the AI stuff, but one thing I know that's a little bit annoying that it's actually a feature that C has that Rust doesn't is C has bit fields. So you can take like a fixed width type, like a uint32, has 32 bits in it. And you can actually say like, I want to set bit 23 to 1. And C has a relatively nice syntax for defining structs that really compiles down to just a uint32, and you can reference individual bits and you can set them directly.
There must be a crate for doing that.
There absolutely is a crate for that.
There's probably like some kind of macro.
There absolutely is a crate for that. But it is one area where people that program in C all the time with this kind of stuff, like they use that feature extensively. And if you're used to that feature, going to Rust and needing a crate can be a little bit jarring for some folks.
Okay. Any other questions? Going once. Going twice.
probably put everybody to sleep.
No, I just don't have any questions. It was a great presentation. You answered questions I didn't know I had.
Yeah, that was a great presentation. Yeah, so thank you. Thanks for the presentation. And we've got some comments, I think. We have a couple questions here.
How to write ISR in a Rust runtime environment? Sorry, what's ISR in this context? Oh, okay. Yeah, so that's going to be a little bit more hardware specific. So hardware will typically have like a register address that you need a function of a particular type that it can call, and so then you can say, oh, when an interrupt is fired, call this function. The function will figure out what went on. I don't have any examples of how to do that. I haven't actually done very much of that, but it is possible. And so the other question is specifying to the linker. So you have a couple options. One is linker scripts, but if I go back to the LED example, yeah, okay. I'll share my screen again here. So if you want to know, so there is magical compiler syntax for things like sections and where you want to put stuff. This is mostly, well, yeah, it shows up a lot more embedded than it does for desktops, so it's totally valid. So this was the LED. What we're looking at here is the expansion, this Arduino HAL entry. And you can see there is actually a link section here. And so for this particular device, there's apparently 10 init sections, 0 through 9, where most, like 0 through 8, are mostly taken up by hardware stuff that's hard-coded. But init 9 is where your application shows up. And you do have to specify, this is where I want this to go. And so, yes, there is a special compiler syntax to do that. So, yeah, you have some options. Basically, just Google it up. There is a Rust embedded book online that actually I should link to that might cover some of the compiler features.
Did you answer both questions? Or?
I think so.
Anything else? Going once, but twice. All right, cool. Oh yeah, once again, thanks for the presentation. It was excellent. I learned a lot from this. I'm gonna go back and go over this recording in the future, I think, when I start working on my project, because there's a lot of good tips here. Didn't know about like the strings, like the heatless stuff. It's been interesting.
Yeah.
Good to see like that's how that kind of stuff works. But yeah, this is the part where you're just gonna hang out. If anyone has any hello. If anyone has any like additional questions, or if they want to like show off my project, or
It's a question.
okay, go ahead. Yeah.
How do you access the chat in Google Meet? I can't find it. I mean, when somebody sends a message, I can click on it and join the chat, but like, where's the chat button on?
What do you mean? You mean like just the
yeah, in call chat, like
yeah, it's in the bottom right. It's the same place
Yeah.
it's always been.
Bottom right.
I
There's a
see.
little
Okay, so it's just gone for me then. Cool then.
What?
Might.
Here, are you on, or what are you? Are you on like a
Chrome. I always use Chrome for the meeting.
No, but are you on like a mobile device?
No, my computer. On the phone, I can find it on the phone. I can't remember where, but I get it. It's just It's okay. It's all good. It's just me then. No worries.
That's weird. But okay, sure.
Yeah, it's fine. I was just wondering. I was like, is it just me or did they hide the button or something?
I don't know. Maybe you've got some weird like browser plugin installed that like hid it or something. I don't know.
I have no plugins installed. I don't use this browser. I only use it for Google Meet.
Oh,
Google just doesn't like you.
yeah.
Yeah, it's okay.
And it's fine.
I'm okay with it. I was just wondering if there was like some where you had to go to find them. Like, I can't figure this out.
You'd think Google's browser would work with Google's applications.
That's
Yeah.
why I use it.
Oh boy.
But
Oh yeah.
I think-
Well, one quick thing I want to raise before before we move on.
Right.
Slides. You're gonna submit them to our repo, right?
Yep.
Okay. Cool.
Yeah, always PM.
So yeah, we do have a repo for all of our past talks. I think it's on like the GitHub Vancouver-RS/talks page. There should be a link in the meetup description, I believe. So yeah, if you want to get a hold of the slides, you can get them there. And we also have a Discord where any links that are posted in the chat here will be copied to. I guess I'm gonna have to do that because Chester doesn't seem to have access to the chat. So yeah,
I can. I have access when somebody sends a message. So right now I have access.
Okay. Weird.
But we probably don't need to do that because we can just upload the thing from the recording. When we turn on recording, it also records the chat.
Oh, okay.
Yeah, so I'll just wait for that this time because it has a nicer format than my copy and pasting thing that doesn't come out so clean.
All right, sure. Then yeah, we can just wait for that. Yeah, the Discord link. If you don't know, let me see if I can find there's an invite link in the server. I'll copy it.
That's one. And the invite link, I got it.
You got the invite link?
Yeah, let me which one? Copy link. This one.
Excellent. Yeah, there we go. So if you want to join our Discord for this community, there you go. Here's the link. Focus on that. Oh, and the YouTube channel. The YouTube channel where the recording goes. I forgot about that. I also need to get that.
All right, I'll drop that in there too.
You're so prepared.
No, it's all on Discord. I'm not. I'm just
Wait,
copying it from this to Discord. Yeah, there's an
Wait,
about.
really? The link
There's an
says
about
that-
channel.
What?
It's right next to the
Oh,
invite
yeah,
link channel.
Wow, that was posted in like 2023.
Yeah, it's been there since we created Discord.
Oh wow, crazy! I didn't know that you had it there.
I didn't know either. I just like I would put this here. That's the thing I would do. And I looked and it was there. I was like, okay, yeah, there we go.
Nice. Okay, cool. Yeah, there you go. Or you can just join the Discord. Apparently, everything's there.
Everything's there.
Well, not everything, just all the things you mentioned.
That's basically everything. Everything except for the actual like, meetup event details.
Oh, is that not there? I
Well, I guess
copy
that's technically there too in the announcements, but like you have to look at the actual meetup page. For the-
Oh no, it's not there. You're right. No, it's not there. Oh no, it is there. Okay, it's like the third one or fourth one, something like that. Whatever, it's there. I guess I didn't copy that one because I figured, everybody got here through Meetup most likely.
Yeah, probably. Like that's where that's where the link is. Except I guess I also email out the reminder, and the reminder also has the link to the meetup room. So,
Yeah,
but then you have to RSVP through meetup to get.
exactly, to get the link. I think even like this weekend Russ still sends out the link to the Meetup.
Yeah, that's about the extent that they get involved.
Still, it's nice of them.
It is nice of them, yeah. I mean, I don't even ask for it.
right? Because we don't actually have to submit it every time.
No, yeah, they just automatically do it. They're just they're just nice like that.
They're great. They're amazing. Because I'll be honest, I don't know if I'd have the patience to do it every week.
Yeah, like having to go and like submit a PR or something like that.
I mean, I used to do it like when I used to watch a lot of YouTube. I would submit YouTube videos that I thought were interesting on Rust. Um, but now that YouTube, I don't know. I think it takes too much of my time, so I try not to watch YouTube.
Fair.
At first, the ads used to annoy me enough that I would leave, but now I've gotten accustomed to the ads and I just suffer through them and wait for my stuff to start back. I'm like, oh no, this is bad. I need to stop.
Okay. I have uBlock Origin, and like what I've done with it is I've configured it so well. First of all, it automatically just blocks the YouTube ads, but I just have it zap literally every single YouTube recommended video, so I can't see any recommendations ever. So my front page is just blank. The sidebars always blank when the video finishes. That's also just a blank screen, so I never get distracted.
I don't know if that's better or worse.
I like it. I personally like it. If I
Yeah.
look for something in particular, I'm just gonna search it up.
Right, fair enough. I mean, I've learned so much from all those recommended things, but it is a problem. So I guess I have done the same thing as you. I just stopped using YouTube altogether instead. Yours is actually better because you still get to use YouTube. I don't get to use YouTube at all. Same outcome.
Yeah, well, that's the thing, right? It's just like, oh, if I don't want to get like sucked into the rabbit hole of like I'm clicking this and I'm clicking this video and then I'm clicking this one, then
Right. And shorts, oh my goodness, those are bad because you can skip the ads.
Oh, I don't see any shorts at all.
It's probably for the best.
Yeah. I wouldn't say I've seen a lot of value in the shorts. Recommended, I have seen things that were adjacent to what I was watching that I thought was interesting.
Yeah.
The advertisements are always annoying.
Mhm. I mean, you can just have like a base ad blocker and it'll just get rid of those ads.
Yeah.
No, I like the ads in that they break the algorithm a little bit and they're like, oh, I can escape. Run.
Oh, I see.
Oh, okay. Fair.
Especially when the ads like 2 minutes long. I was like, oh well, for sure I can leave in YouTube now.
Interesting way of handling that. But okay.
Yeah, so
Well, timers don't work because I'm like, okay, 2 more minutes. This is almost finished. Timers don't work. So the ads, those work because they actually stop me whether I want to. I'm like, oh well, since I've stopped.
Okay.
Yeah,
Yeah, you do you.
fair enough. I can't say I recommend it as a strategy. It doesn't always work.
All right. And also, I think next month we have another talk coming up.
Yes, I think the next one's on Nusha.
Well, yeah, who's doing that?
As soon as I found all the things I needed from the documentation, I stopped reading it, which is, I guess, fine. But I was hoping to finish it because I was like, I always do this where I get just some of it and I leave the rest. I was kind of hoping to finish it this time.
Oh,
I was
there we go.
showing my brother how to use eGUI today, and I was like, I remember why this was so cool the first time I used it. And now I just like, yeah, Nusha is pretty cool. I've been using it as my daily driver since last Meetup, so I guess about a month. And it's been great. It's not the same as Bash, so I did have to do a bit of adjustment for my aliases and that kind of thing because I still want Bash to work in case I need Bash to work. So I want to have one list of aliases. I don't want to have to, copy and paste it each time. So I wrote a new shell script that converts my Bash aliases if there's been an update. It was actually pretty cool. I was like, I feel like I should publish it somewhere. People would want this. I was like, who would want this, Chester? Nobody wants this.
What was that? Oh,
Somebody's phone.
yeah, I think he has.
Yeah, I've learned things from other people's shell setups. Occasionally, I like copy them entirely, but people's configs. Sometimes you're like, oh, I didn't know that existed.
Yeah, I've been kind of hesitant about jumping into new shell because, like, a lot of my projects. Hello.
Hello?
Yeah.
Oh, I'm using it on the wrong thing. My bad. Sorry.
Okay. Yeah, no. I've kind of been hesitant about jumping in a new shell because like a lot of the projects I've worked on, like my team is so used to Bash that they just only like Bash scripts and just like I know how easy it is to like use new shell with a project that's like entirely comprised of just shell scripts.
It's not.
Yeah. So I'm just like
Doesn't run bash scripts.
it's the teamwork aspect that makes it kind of hard.
Yeah. It's so easy to switch back to bash if you need bash that I don't mind.
Yeah, I guess so.
Yeah, I found for myself, like many years ago, for a variety of reasons, I switched to ZSH instead of Bash. And, I like it. ZSH is not the new cool kid anymore, but, it has been consistently better than Bash for a long time. And what I found is that it just, like, when you're in that kind of environment, it just means that you have to be a little bit more careful at like top of all the shell scripts. You need to make sure that they have the proper hash bang, so it does bin bash as opposed to just kind of assuming that bash is running.
Yeah.
And there's like a bit of a initial pain point, but then after that we can kind of run with any other shell. And when you run the script will run bash. Right? So
Yeah, that's a good idea. If I put shebangs in front of my scripts, then actually they probably still work. I don't do that. That's why they don't work, I guess.
Yes. Shebangs are great. Like,
Yeah, I use them for when I use Rust scripts, right?
Yeah.
Which is how I ended up learning about them because I was like, okay, what's this thing about? Because I've always seen it. I just wonder why people put it. And I was like, it works if I don't put it. I don't put this anymore. And hence, none of my scripts have it. Which is why I said, Jonathan, that doesn't work very well. But I guess if you put the shebangs, you'd be all right.
Oh, interesting. Yeah, maybe I'll give it a shot then. I mean, that's the only reason why I've ever like kind of shied away from it. Other than like I just don't spend the time. I don't invest the time into looking into it.
Switching to ZSH was much easier, though. I did that a couple of years ago. Okay, I can check when, it doesn't matter. But the point is that was a much easier transition because it was very similar to Bash, except less bad.
ZSH is like the default on my Mac. Like when I
yeah, definitely. I use ZSH. Used to use it
for years. Yeah.
before the show. I was happy with ZSH. Only problem I had with ZSH was that you couldn't put inline comments. So you couldn't put a command and put a comment on the same line by default. But it was a setting. I switched it and it was fine. But that was the only thing that was annoying because I like to put comments on my commands, especially since the commands get saved in history. So I can find them again and make sure I use the right one. Because I can't remember the command. That's the whole point. I can't remember the command. So I'll search for something in the comments.
Yeah, that makes sense.
Yeah. Oh, I just looked at the time. It's already 7:30. Wow. Time flew. You know what we should have done? We should have plugged this microphone into your machine, and then that would have been a lot smoother.
Exactly.
That would have been a lot easier.
In the future, we can work on our multi-device setup.
Yeah, or maybe I'll just have it so like presenter always gets the mic, and then that way, whenever they talk, it goes to their webcam. And then,
Yeah, that makes sense.
Yeah, that just is a lot better. This office, like the setup that we have here, has always been kind of jank since the beginning. They haven't really done a whole lot to fix it, unfortunately. But kind of is what it is. But like the HDMI over here, and then the projector like all on the opposite side of the room. But yeah. Final things to talk about. If anyone has any presentations that they would like to do, feel free to hit me up or hit Chester up or just like post about it on the Discord, or you can just pipe up now. Like if you have like a cool project you want to talk about that you've been working on, then we'd be happy to have you. Or we can slot you in for not next month since we already have a speaker booked, but for the month after.
And then once we have an open slot, I think I want to schedule myself to present controlling a mouse in Rust.
Oh,
nice.
Yeah, because I've wanted to learn how to do it for about a year now, and I keep on not doing it. But if I have to present it, I don't have a choice, do I?
Oh, wow.
So I think
Do I have an offer for you?
There's so many things I want to automate, but they're not amenable to automation normally. So I want to, just the thing that will do clicking for me. That's what I really need. The typing, I've never really had a need for. It's more click this, then click this, then click this. Those boring things you have to do like, every month. You have to do it. Click this, then click this, then click this, then click this. I guess you guys don't have that. Okay, I have a lot of things like backing up some stuff and things that there's just no easy way to automate, and I want to automate them. Yeah, and I want something that just if I can click on things, then that would solve 90% of my problems. I already picked out the library and everything, and then I just not making the time to try it.
Well, I'm curious to hear about it. So yeah, if May 20th sounds good for you, then I think we can slot you in for that.
Yeah, sure.
All right, cool. I'll slot you in a little bit later. I'm not gonna do it like
But I mean, if somebody wants to present, don't block the spot for me, right? But if there's an open slot, I'll take one.
Well, there's currently an open slot.
Well, what I mean is that if somebody volunteers for that slot, don't withhold the slot.
I don't see anyone else volunteering right now.
It sounds like you feel like you volunteered too quickly, and now you're
No. It's not that I want to quickly. Is that I what's the word? I already see myself saying, "Why did you do this?" And I'm like, "No, Chester, just do it."
All right. Well, if anyone else wants to present, then you can chime in, or you can send a message on the Discord. You can DM me, you can DM Chester, or you can just send a message on Meetup to one of us. Actually, I check my Meetup messages. I don't know about anyone else.
Yeah, I check them. Well, it sends me an email. I don't check them. It sends me an email, and then I go.
Oh, okay, well.
I don't go to Meetup to check messages. Anything that needs me to check messages, then it has to be worth it. Like I use Discord for work, so sure, I'll check messages on Discord. I use Signal, I use WhatsApp. Those things are just always on.
Mm-hmm.
Other than that, you better be allowing me some way to say notify by email. Otherwise, I'm not going to check it. Like LinkedIn. LinkedIn. If LinkedIn didn't do emails, I probably never see LinkedIn messages. I don't go there just to check messages.
Fair enough.
But it does do messages, so LinkedIn is fine.
All right. Cool. I'm gonna just stop the recording again.